Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series, which are delivered for the benefit of the BSc Physical Sciences students who have got a paper on applied electronics. And the chapter with which we are dealing is on quantum mechanics. And in the last lecture, we were seeing as to how the energy quantization occurs for the problem of a particle in a box when you apply the Schrodinger equation, the most fundamental equation in quantum mechanics. The contents of this lecture are as follows: eigen values and eigen functions of a particle in a box, potential energy of the simple harmonic oscillator, vibrational spectroscopy, Schrodinger equation for one dimensional harmonic oscillator, Hermite differential equation, and the solution for the problem. And in continuation with what I have been telling you in the last lecture, we were seeing the problem of a particle in a box, by which we mean an electron bound to an atom or a molecule or a solid or a nucleon bound to the nucleus. They are all bound state problems. These particles being microscopic in nature, they are quantum particles, they are to obey quantum mechanics. By quantum mechanics we mean discreteness, and we talk of eigen values, and we ended up in the last lecture with the expression for the energy of the particle in a box, which goes as given at the bottom: E is equal to n square h bar square pi square by 2m into L square. What is L? L is the box, one dimensional box. M is the mass of the particle. The particle may be a nucleon in a nucleus or proton or electron. H bar is nothing but the unit of angular momentum. It is a Planck's constant divided by 2 pi, that is also a constant, pi is a constant. Therefore, the point to be noted is the energy will be multiplication of some constant. The entire thing can be made as some C h bar square pi square by 2 m L square, take it as C, a constant times n square. So, energy is getting quantized. You have this as a C, n is 1 means it is C, n is 2 means n square, that is 4 times C, n is 3 means 9 square, 9 times C. Therefore, the energy is getting quantized automatically. That is what I am showing here in this diagram. E1, the lowest energy, in the expression you have got n equal to 2, the energy will become equal to 4 times E1. E1 is by constant, maybe C, right. It is first is 1C, then 4C, then what 9C, 16C. So, there are the things that I am showing here. So, the important point to be noted is, unlike in the Bohr atom model, where the quantum number n that I had finally for the energy of the electron, the energy of the electron which is bound in the hydrogen atom is given as minus 13.6 divided by n square. How does n come? How did n occur in the Bohr's quantum model, Bohr's atom model? N was introduced by a postulate. What is a postulate? MV, or what is MV, or the angular momentum should take integral multiples of h bar. That is what Bohr made as a postulate. So, remember the n that we had in Bohr's atom model was introduced by a postulate, but here you see that n is coming automatically. How does it come automatically? Via the boundary condition. The boundary condition that you impose, it gets you n. You had sin k l equal to n pi, k l should be equal to n pi, that is the mathematics. Therefore, n is coming automatically, right. Therefore, the energy is quantized. These are the discreteness in the energies. The energy of the electron will take only certain finite values, unlike the mouse which can have continuous values. Is a classical object, the book is a classical thing and this is a classical thing, they can take any value, but the electron in an atom or in a molecule, you will have only discrete values. There is a sense of the problem of a particle in a box. By a particle in a box, you should not feel it is a trivial problem, it is a problem which is of not very great significance. I will tell you the significance of the problem. The eigen function, in any problem you get the calculate eigen value and also the eigen function. The eigen function, that means the state of the electron, is given as psi equal to a sin n pi l by l into x. That is the wave function or the eigen function is given in the following form. We will deal with the eigen function in a detailed manner and the meaning of it will be known in the case of hydrogen atom, which I will be dealing with in the lectures to come. But here also I will show them the diagrammatic representation of psi and psi square and so on. So, here comes the discrete eigen values which I showed it earlier. The electron or the particle in question in a box will have discrete energy values. They are the wave functions, right, the eigen function, right. What is measured in the laboratory, as I told you, eigen functions cannot be measured. You can just imagine a string. You assume I have got a string, I can make they are the end points. I have got a string, the one end, the another end, you got a string. Imagine I got a string here, I can make the string to vibrate. I can have either this or I can have one loop or two loops and so on. The displacements caused in the case of a string, or when I drop a stone in a pool of water, the water wave is there, the water wave can be observed, the displacements can be seen. But in quantum mechanics, these displacements psi cannot be seen. What can be measured is only the complex conjugate multiplied by psi. Psi square can be measured. What can be measured in the laboratory is psi square. And again, this diagram is of considerable interest. It shows the energy eigen values are proportional to the k values. E equal to, I showed it in the last lecture, h bar square k square by 2 m. Therefore, your the energy values, your k1, k2 can be assumed to be something like n taking values 1, 2, 3 and so on. So, the k shell, l shell, m shell, the electron energies will be something like what I am showing here. The energy values will be E1, E2, E3, they will be given in terms of k1 or in terms of n, because you have got the energy given in terms of n. N is something like a quantum number. So, the energy values are discrete. So, the point which I want to tell you is we did this for a problem of a one dimensional box. I told you about photoelectric effect or solid state materials. You take a semiconducting material, the material you got in your cell phone. Now, the cell phone has got a silicon chip, and so the expression that I had for a one dimensional case can be extended to 3 dimensions. That means a solid in a semiconductor or transistor. Then the above expression can be extended. The expression that I had for E for a one dimensional case can be extended to 3 dimensions, in which place I will have instead of n, I will have nx, ny, nz. N square will be replaced by nx square plus ny square plus nz square. Nx, ny, nz, like n will take only integral values. By doing this, I will obtain what is called the expression for density of states, how many energy levels are there in the valence band or in the conduction band. You know, in a semiconductor or the whole functioning of the cell phone that you have got here, or the function of a solar cell, or the function of anything that you have got here. I have got a computer, the working of a computer wherein you have semiconductor chips, the working of a computer or the solar cell or a cell phone, everything will depend upon how electrons behave in solids. So, to understand the current voltage characteristics, right, the junction, the diode or a triode, in general, to understand or to calculate the current flowing in a semiconductor, in a cell phone, the IV characteristics depends upon how many electrons you got in the valence band and the conduction band and so on. These things can be obtained from the particle in a 3 dimensional box, electrons in 3 dimensional semiconductor material. Therefore, the problem that we have been discussing, I will ask, is it a trivial problem? The particle in a box, one dimensional box, is it a trivial problem? It is not a trivial problem, it is a very important problem. It has to be extended to 3 dimensions. For the sake of simplicity at the BSc level, we stop with the one dimensional box, but it should be extended to 3 dimensions for a semiconducting material. Then you have to find the number of electrons in the valence band, conduction band. Then you have to calculate the current flowing in a semiconducting material. Therefore, the continuity of the problem, particle in one dimensional box, 3 dimensional box, density of states in conjunction with what is called the Fermi-Dirac distribution function. All these things ought to be applied, and in totality it will give you the current, and the current when you apply a forward bias or a reverse bias. So, you can calculate the current as a function of voltage. The IV characteristics will give you as to how the semiconductor will act as a rectifier or amplifier or oscillator. With this, we pass on to, that is what I am showing here, the flow of electrons in semiconductors. You have got a, the valence band and the conduction band, the electrons in the conduction band and the holes in the valence band contribute to the current in a semiconducting material. And these things you will be studying in maybe in a separate paper on electronics, practical electronics or quantum electronics. We now pass on to the next problem, which is to be solved using the Schrodinger equation, which is known as the simple harmonic oscillator. What is meant by simple harmonic oscillator? Where do you find that? Now, whenever you study any problem, you should have an understanding as to why should you read the problem and what exactly you are getting out of the problem. Now, straight away I will tell you, you have the vibration spectroscopy. The vibration spectroscopy is the vibration energy levels will be obtained from the problem of harmonic oscillator. What is this? I am getting light here from, you got the whole room having a lot of tube lights are there, I get a lot of light. How do you get the light? It is from the electronic excitations. It is called a electronic spectroscopy. Electrons are found in different levels, energy levels, as I told you just now. The electrons are found in different energy levels. The excited electrons, when they come down, they shine light, right? The energy difference is emitted as a photon, right? Photon is light. So, the mercury vapor lamp, the mercury atoms are excited by the electrical energy. The excited electrons come back to the ground state. During this process, energy is emitted, that is light, that is incident on me and incident on you and all. So, that is electronic spectroscopy. Similarly, the spectroscopy you have, you talk of vibrational spectroscopy and rotational energy levels, the vibration energy levels and then the rotation energy levels. I will do or discuss the rotation energy levels in the lectures to come. Now, we will talk about the atoms which are vibrating in solids. So, the first question that I have, the first question that I pose to you, you have in any solid, you take a solid here, right? You got a solid material, you got a solid is composed of atoms. I will ask the first question, what are the atoms doing in solids? You know, in a gas, what are the molecules are doing? They are moving. You got in this room, you got air. What about the air molecules? They are moving here and there, right? You all know the air molecules will be moving here and there. When I am talking, how does one hear the sound or the noise I am making? You know, the water air molecules are taking the energy which I am giving as output. My sound is transmitted, whatever I am talking is transmitted through the air molecules. So, you got molecules which are moving in the room. Similarly, in the solid you got atoms. What are the atoms doing in solids? If I ask the question, what are the atoms doing in solids? At all temperatures the atoms are vibrating, right? What are atoms doing in solids at any given temperature? At all temperatures the atoms are vibrating. Especially I will ask the question, at 0 Kelvin what are the atoms doing? Are they at rest or doing something? The Max Planck, the person who initiated quantum theory, he said at 0 Kelvin the atoms will come to rest, which is completely wrong. I will repeat once again, it is Max Planck who developed the quantum theory. This quantum theory is now called old quantum theory, because of the fact that according to Max Planck's theory, the energy of the oscillator, the energy of the atoms, they will be given by an expression E is equal to NH nu, and n will take values starting from 0. At absolute 0, n will be equal to 0, h is the Planck's constant, nu is the frequency. You do not worry about the frequency, the important thing is n becomes 0, that is the ground state, the lowest state. When t equal to 0, n will be equal to 0 and therefore, E will be equal to 0. The atom will stop vibrating, right. If the atoms stop vibrating at the 0 Kelvin, then you know something will become wrong, you know, that is not the real case. Therefore, I ask the question, is the above expression correct? Therefore, the old quantum theory which was developed by Max Planck is wrong, and you are going to see a different expression from the lecture I am delivering now. I am going to finally show that E is not NH nu, it is something different, right. What is the difference? That is the real thing, that is what is shown by experiments. The old quantum theory has led to a wrong result. It says that 0 Kelvin the atoms come to rest, which is definitely wrong. So, we pass on to quantum mechanics, and the reason why we are studying this problem, why we are selecting the problem, and is to understand the so called vibrational spectroscopy. What is meant by vibrational spectroscopy? As I told you here, I told you about the electronic spectroscopy. Similarly, here you have to know the vibrational energy levels, vibrational energy states. So, they are the eigen values, they are the, this is one eigen value, this is another eigen value. So, the eigen values for the oscillators, what is oscillator means, what it is oscillating, the atoms are oscillators. So, we are talking about simple harmonic oscillators, they are harmonic, they are in a harmonic manner means there is some kind of resonance, the atoms are vibrating, you got atom here, in a solid in a continuous row of atoms, they are vibrating, and the vibrational energy levels are the one which one tries to calculate in this problem. If you have calculating these energy levels, you know, when the atom is coming from this energy state to this energy state, the difference in energy will be coming out as a photon, giving rise to either a Raman scattering, you get a Raman line, or anti-Stokes scattering, whatever be the thing. With this problem being solved, you can get the vibrational energy levels and hence the vibrational spectroscopy. So, the atoms and molecules are vibrating, atoms and solids are also vibrating. Okay. This is the simple harmonic oscillator. In classical mechanics, we often treat small displacements from a stable state of equilibrium in terms of simple harmonic oscillations. So, you take a case of molecule, water molecule, or HCl, HNCl, the two atoms, the hydrogen and chlorine, irrespective of the number of atoms in a molecule or in a solid, you have a spring. What is the meaning of the spring? The spring is the binding. It shows that the spring constant, the Hooke's law forces come into operation. Anyway, the point is the atoms are bound to each other. The binding is shown by means of a spring. Do not search for a spring inside the solid. You do not have the spring refers to the attractive potential energy operating between the two atoms, H and Cl in a molecule, or H2, this may be some other molecule having 3 atoms. You can have a n dimensional solid having n atoms. So, such harmonic oscillation, they should be vibrating, right. At any given temperature, you assume the atoms to be vibrating. Such harmonic oscillators are also very important in quantum mechanics, where they can be used to describe the vibrations of a molecule, the atoms in a molecule, or the vibration of atoms in a crystalline solid. So, you make use of the classical mechanics and try to write down the potential energy of the system. The important thing is, in any problem in quantum mechanics, the input, as I told you, is the potential energy. The potential energy experienced by an atom which is held by means of neighboring atoms, the Hooke's law force will come into operation. The potential energy can be written as, how do you write force? Force is minus kx, k is the spring constant. So, the potential energy will be half into m mass of the atom, omega is the angular frequency, x is the position coordinate of the atom. So, this is the potential energy experienced by the atom in a molecule or in a solid, and now we have the Schrodinger equation. You have to substitute this V here in the Schrodinger equation, and then you try to solve the equation. Now, unlike what I did in the particle in a box problem, what did I do? In the particle in a box problem, we made V equal to 0, but now we have got a finite potential. The problem is going to be complicated, and we are expected to do the problem in a serious manner, in the sense you do not give the outline, but in a detailed description should be done. So, you come across a considerable amount of mathematics which will involve the Hermite's differential equation. The Schrodinger equation will now become, the potential energy is given as half m omega square, that is what you have here. Now, for simplifying the equation, you introduce the following substitutions: square root of m into omega by h bar into x. X is the displacement suffered by or experienced by an atom, E by h bar omega, okay, and you after making these substitutions in the above expression, this expression gets simplified into in the following form: half into epsilon square minus d square by d epsilon square multiplied by psi into epsilon. What is epsilon? Epsilon is the position coordinate. You know, in the Schrodinger equation you write psi as a function of x and t in the time dependent equation. Now we are discussing about time independent equation. Therefore, this epsilon is something like displacement. So, this epsilon that you have got here, it is nothing but the energy of the particle. So, you know the Hamilton E into h into psi will be equal to E into psi. This E is the energy, this you can call as epsilon, hereafter I will call this E. Now, equation 1, an eigenvalue equation, can be solved analytically either by using a power series expansion or by an operator technique. So, the equation 1 can be rearranged in the following form: d square psi by d epsilon square plus 2 E minus epsilon square into psi is equal to 0. This cannot be solved directly using power series method, but by taking the substitution you write psi epsilon is equal to y into as a function of epsilon into e to the power of minus epsilon square by 2. You make a substitution for psi that you have got here, and now the expression becomes, it takes this form which is known as the famous Hermite's differential equation, which goes as d square y by d epsilon square minus 2 epsilon into dy by d epsilon minus 1 minus 2 E is the energy of the particle or the atom into y is equal to 0. This can be solved by assuming a power series solution. You have a polynomial, right? You write y as a function of epsilon equal to a naught plus a 1 epsilon plus a 2 epsilon square and so on. So, that is you have sigma of the same thing, sigma of a k into epsilon to the power of k, a power series, right. You write this y of epsilon as a polynomial and a k are the coefficients, a 1 a naught a 1 are the constants. Hence, equation 5 can be written down like this: dy by d epsilon and d square y by d epsilon square. The expression for y, these things are to be performed as is shown in this slide and substituted back in the expression, and ultimately they will lead to the values of epsilon, the eigen values and the eigen functions. These things will ought to be seen in the lecture to come. The summary of this lecture, as far as we have done, goes as follows. The atoms are vibrating in solids. They are the examples of harmonic oscillators approximately. The study of the problem is able to explain the vibration spectroscopy of molecules and solids. Unlike Max Planck's old quantum theory, we find that the energy eigenvalues are shifted by some constant value which will be called as 0 point energy, and the questions with regard to this lecture are the following. Question number 1: why does one study the problem of simple harmonic motion? Give the potential energy expression for an atom. Describe the mathematical steps involved in the problem. What are its eigen values and eigen functions? With this we come to the end of this lecture, and the rest of it we will see in the lecture to come. Thank you.